With the rise of tablet computing, interface designers have begun focusing on more intuitive methods of input. Perhaps one of the most natural inputs is through writing. After all, who doesn't know how to hold a pen? But turning a person's handwriting into something meaningful, as opposed to just squiggles on a screen, is not an easy task. Computers excel at performing exact sequences of precise commands, not matching patterns. The human brain, however, excels at picking out these patterns. Perhaps a computational model similar to the brain could help us detect handwriting. A human brain is made up of neurons. These neurons are relatively simple. If they receive enough chemical signals from other neurons during a short period of time, they trigger, releasing stored up chemical energy to send signals to all other neurons connected to it by its axon. We can construct a similar mathematical model as follows. First, we get a threshold value that causes our neuron to fire, and a special function to tell us how strongly the neuron should react to the input. These functions are called sigmoids, which look like this. Next, we add the inputs and assign weights to each of these to determine how strongly they should influence our neuron. We take the inputs, here they're between 0 and 1, we multiply them by the input weights, add up the weighted values, and compare it to the threshold. If we're greater than the threshold value, the neuron outputs the sigmoid out of the weighted sum of inputs. We can now form a neural network by chaining these neurons together in layers. Each layer feeds its result only to the layer in front of it. Since we're interested in handwriting recognition, let's take a letter and break it up into a grid. Each cell in the grid becomes an input to our network. We now add a hidden layer to aid in the computation, and then an output layer, with a neuron for each letter. If we feed the grid to the network, we should see exactly one neuron light up. Of course, the behavior of the network is completely determined by the weights and thresholds that we've set. So, how do we pick the right values? It turns out we don't. We let the network pick its own values. We do so by training it. One way of doing this is providing the network with a letter and asking it which letter it thinks it is. Based on how far off the network's answer is from the real answer, we can use a technique called backpropagation to adjust the weights and thresholds in the right direction. Backpropagation works by calculating the error and using these equations to determine how responsible each weight and threshold is for the overall network error. If we continue this process again and again, the weights and thresholds will settle to a value that allows the network to behave as we want it to. In a sense, through this supervised instruction, the network is learning. Using these techniques, neural networks in specific configurations can approximate any function you might want. These networks are particularly useful when you know the answer you want from any given input, but you don't know exactly how to calculate it. These networks have enabled computers to become much more proficient at detecting patterns, and all because we modeled the technique after the original pattern matchers, us.